Hello, my name is Beth Dixon, and this is a video series on Vicki Borlaug's PowerPoint presentation on the confidence interval on the mean. For this PowerPoint, we are working with X being normally distributed with a population standard deviation or sigma as a known value or approximation for large sample size with n greater than 30. I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos, and this is part 2 of the series. In part 1, we covered on how to find our Z alpha sub-alpha scores. Let's do example number 1. A company manufactures parts. A random sample of 40 parts is taken and the length measured in centimeters. The sample has a mean length of 163.1 centimeter. Assume the lengths are normally distributed with a standard deviation of sigma equals 44.6 centimeters. So our important information from this problem is we have a sample mean or X bar of 163.1. The sample has a mean length of 163.1. We have a sample size, a random sample of 40 parts, so n equals 40. Now, notice that we can assume that the lengths are normally distributed with a standard deviation of sigma equaling 44.6. So sigma equals 44.6. Notice that is not a sample standard deviation, but with the use of sigma, that is a population standard deviation. It is very unlikely that we would know the population standard deviation or sigma when we don't know the population mean or mu. But it is the easiest case to do mathematically, and we will learn how to do the X normally distributed and the sigma unknown case in a future section. So let's do this case first and proceed from here. So there are our numbers again. X bar equaling 163.1 centimeters, sigma equaling 44.6, and n equaling 40. What is the best estimate of the mean length mu, or the population mean, of the parts? Well, the best estimate we have is that sample mean X bar of 163.1 centimeters. That's our best estimate. Is the sample mean length the same as the population mean length? No, probably not, but hopefully it is close. Well, the question then becomes, how close? Well, the goal of the confidence intervals on the mean is to find out how close your sample mean is to the true population mean. When we learn how to do confidence intervals on the mean, we will be able to complete the following sentence. I can say with 95% confidence that the mean lengths of parts is between blank and blank centimeters, and we will be able to fill in those two blanks. The first blank we will call the lower confidence limit, or LCL. The second blank will be our upper confidence limit, or UCL. And you will be able to choose your level of confidence. Well, the problem will tell you what your level of confidence is. Confidence intervals are always two-tailed. because you want to know the lower and upper limits. Confidence intervals are always two-tailed because you want to know the lower and upper limits. Confidence intervals are always two-tailed because you want to know the lower and upper limits. Confidence intervals are always two-tailed because you want to know the lower and upper limits. Do you think this is an important statement? Well, because we repeated it so much, it must be. So I think it's an important thing to remember. Since confidence intervals are two-tailed, we will put the alpha risk in each tail. So that alpha variable we just introduced in the first video becomes the amount or percent we're willing to risk being wrong. We will put this in a left and right tail. So we draw the curve and put half of the alpha risk in the upper tail and half of the alpha risk in the lower tail. The z value with alpha divided by 2 area to the right and a negative z alpha sub 2 due to the symmetry of the bell will then be to the left. So the distribution of the mean lengths of parts. Remember, in the example that we are talking about, we want to be 95% confident. That means that we are willing to risk 5%. There's a total of 100%, so 95% confident leaves us 100 minus 95%, leaves us that 5% that we're not sure about, that we're willing to be wrong, or that we're willing to risk. We will take that 5% and divide it equally between the left and right sides. We're willing to put that on the upper and lower sides equally. So that gives us 5% on each side divided by 2 would give us 2.5% on each side. And it would be unusual to get a sample mean in the tails of this area. The 95% would be usual or ordinary, and in the tails is where we would consider it to be unusual, out of the ordinary. Based on your sample mean, 163.1, what might the population mean be? Where does the population mean go? Well, it could fall anywhere along the number line. Notice we could move it up and down anywhere. It would be unusual to have it in the tails, remember, but it could fall anywhere. We're not sure of the one place that the mean goes, but we can give the values that is probably between based on the sample mean of 163.1. Again, where is the range, or where should it go? Let's look at how high the population mean might be. What is the upper confidence limit, or the UCL? Would it be probable for the mean to be as high as it is here? Well, if the mean is as high as it is here, that would mean that the x-bar, or the sample mean, would be here. And notice that that's in the tail, and if it's in the tail, that would be unusual for the x-bar to be as far down as it is and be in that red zone of the 0.025 of this left tail. So the sample mean is in the red zone, or the shaded region, or the dark side, and that may be anything that your teacher may call it. And these are those are not mathematical terms, but they're descriptive nonetheless. Values in the tails are unusual. And it would be, if the mean was here, it would be unusual to get a sample mean of 163.1 because it's in the tail. A sample mean of 163.1 would be unusual if the value of mu was as high as it is here. If the mu is here, then x bar would be here, and that would be an ordinary value. It would not be unusual to get a sample mean of 163.1 because it's not in the tail. So this would be in the range of good values for mu. The sample mean of 163.1 would be an ordinary value for this mu. So where does it change from being ordinary to unusual? It changes when that x bar hits the red zone or hits the tail. This is the place where the sample mean would change from ordinary to unusual. So this becomes your upper confidence limit. And that we will call x bar plus E. And we'll define this E as we move along. But notice it's the distance between the center and the tail. X bar plus this distance between the blue mark and the black mark. The distribution of the mean lengths of parts. So the population mean is probably not over here. Why? Because if it goes any further over in this direction, it would then become unusual to get a sample mean of 163.1. Let's look at how low the population mean mu might be. What is the lower confidence limit, LCL? Would it be probable for the population mean to be as low as it is here? If mu was here, it would be unusual to get the sample mean of 163.1 because it is in the tail. Sample mean of 163.1 would be unusual for this mu. If the mu was here, it would not be unusual to get the sample mean of 163.1 because it is not in the tail. The sample mean of 163.1 would be ordinary value for this mu. And where does the sample mean change from being ordinary to unusual? At this mark here. Again, the place where the sample mean would change from ordinary to unusual, and that is going to be called our lower confidence limit. And in this case, since it's below the X mark, we will mark it as X bar minus E. Notice it's the distance from the tail to the center. Let's circle the correct answer. True or false? The sample mean is always the same as the population mean mu. That is false. But it is usually close or far away. It is usually close. The confidence interval contains mu values that would have our sample mean 163.1 as an ordinary or unusual value. As an ordinary value. And I'm running out of time, so as much as I hate to stop in the middle and just cut off, I am approaching the end of my 15-minute mark, so I'm going to stop here and I will pick up exactly where I left off. Thank you for watching.